Okay, so what is a vector? A vector is something that has magnitude and direction. So magnitude and direction, that's what we're dealing with. The direction as described or depicted in this diagram could be something like this, and its magnitude is described by the length of this. So something that has magnitude that is smaller could be something like that, or greater magnitude can be something like that. And a couple of things to be aware of with vectors is I can technically say this black page here is described as free space. I can technically move this same vector to, for example, this location. As long as the magnitude and direction stay the same, it is therefore the same vector. If I change its direction, so it becomes like this, let's say I'm keeping its magnitude constant, but I'm changing its direction, then it is a different vector. If I'm keeping its direction the same, but changing its magnitude, then it is also a different vector. I've given this some kind of description here. I've made some level of application by suggesting that one of the types of vectors could be said to be displacement, and the point that it starts at, let's say this point here, I'm calling that Q. That's what Q is here. So it starts at the point Q, and this vector here is describing a displacement to the point R for something along that line. But generally speaking, a vector is something that has magnitude and direction, and its length depicts its magnitude, and its direction, of course, is from a certain point, utilizing an arrow to describe where it's going. If I have used, for example, displacement, I can go as far as saying that, that velocity is displacement per unit second, meters per second, kilometers per hour. So displacement s per unit time. And therefore I can rearrange this, multiply both sides by t. I end up with displacement is equal to vt. So this displacement vector s from this displacement vector can be renamed as velocity times time. And that's all I've done there. I've said instead of using this vector s, it should have some sort of hat on it or something along that line to describe it's a vector. Assume that it is, maybe I have to just make it bold to make it obvious that it's a vector, is going to be now called velocity times time, or vt. Now, that's one way of viewing it, from a point Q to a position in a direction, and this vector could be described as s equals vt. That's one way to view it. Another way to view it, however, is to describe this vector s as let's say t is just a constant. Let's change so that's a constant there. In fact, what I will do is not utilize the same color and say this t here, we're going to call a constant. And v is going to represent the vector of magnitude and direction, as I stated. And so what is happening here is t, let's take this v, let's say v is something like this. V, if t is 1, could look like this. If t is 2, let's say it's doubled. 3, 4, 5, 6, 7, 8, and something like that. If it was -1, it would go in the other direction. So v is the vector in this discussion, and t is a multiple, also described as the number of steps. So that is to say, I can also write this as the t is the number of steps, wherein v is a step. So let's do this one more time. Imagine that v looked like this, and that is 1 step. Then I can say this is when t equals 1. I could do, well, what happens when t equals 2? This one would be when t equals 2. And what happens when t equals 10? Let's just say that this is when t equals 10. Not accurate, of course, but let's say that this is t equals 10. And finally, let's also do when t equals, let's say, -2. It would look like this. So this is when t equals -2. And it is multiplying the vector v in a certain way. So it's multiplying the vector v. So we can say that v is a vector and it's being multiplied by t to produce this kind of structure. But what if we wanted to instead just describe the line itself? So what is the whole line rather than this vector? we could go back and say, well, what if we wanted to describe the line itself from just straight across? How do we describe that? Well, first of all, we need to start at some sort of origin, this being our origin. And what we want to do is we want to consider how do we get from the origin to a certain point. We're going to pick the point Q, for example. So let's say we want to get to the origin to the point Q. So that's how we start off. I'm going to say the line R, that's what the line is, the line R begins with a description, and we won't say a description, with a statement as to where a point on the line exists from the origin. That's what we're saying, from the origin. So therefore, from the origin, we go to this point Q, and that's what this here represents. R, the line, is equal to this point from the origin Q plus what we're going to do is we need to move in the correct direction along the line. That would be our V. So let's make that V. Let's say V is like that. There is V. Let's make this slightly smaller for here. There's our V. And what we need to do is we need to do multiple levels of V. We need to multiply V by a certain constant T to move anywhere along the line. So if I wanted to move infinity along the line, then T would be infinity. If I wanted to move 10 along the line, then T would be 10. If I wanted to move 5 along the line, T would be 5. If I wanted to move -1 along the line, T would be -1, and so on. So this is what T technically represents, the steps you move along the line. So therefore, we have the multiplication of T here. And there is the equation of a line. So our equation of a line, therefore, is R equals Q plus VT. And where V, let's make this clear, V is a vector. And Q could be said to be a position vector. Let's say this. Q could be said to be a position vector. What do we mean by that? Because it is from the origin to a point. All right, that's what we're saying. So you can see here that Q is from the origin to that point. That is our position vector. V is a vector, but particularly a vector along the line. Now, let's say, for example, you wanted to move back and forth in time. So I just said, let's make T equals 10. Given that we have R equals Q plus VT, if I've made T equals 10, let's say V is this. Let's say that this is my V. If I've made T equal 10, assume that it becomes 10 times longer, given that in this diagram. If I make T equal, let's say, -5, and in this situation, you can say, I'm saying again, it would be something like that. And so what I could do is, by picking values of T, say I had a computer or some sort, so that I made it so that I could, let's say, on a loop, put in 0, 1, 2, so on and so forth. You see what I'm saying? 3, then you would see that the vector, if I was to throw those values in, would move. Let's say I went to, let's say when I got to 10, I said ... comma 10, and then I started to go back down, 9, 8, 7, 6, 5, ... to 0. And let's say I continued in that manner. So I made this a looping situation. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, 0, 1, and kept going. Then what you'd find is that the vector V would be multiplied up and down like this. And that is one way to see, to view T's capacity. If I was to put minus numbers in here, then it would go this way, of course. Next, what if we wanted to go to 3 dimensions? So let's say we wanted to do 3D. Well, if we wanted to do 3D, then what we would need is the same constructs, but with a little bit extra. First, I'd need my origin, and then I'd need a position vector from the origin to a point, let's say to this point. let's do this point here, like so. This I'm going to call Q, just out of what we've been discussing so far. Let's make that a little bit more visible. So here we can call this Q. And then I need my V, my vector V, which doesn't universally, going forward, it does not universally mean velocity. I'm now just talking about it as a vector along the line. So here we can have V. Let's say V looks like this. Of course, V times T means that any version of time or T I put in, V1, 2, 3, 4, 5, 6, 7, 5, 4, 3, 2, 1, so on and so forth. That will allow for me to move in this dimension here. So let's say something like that. But now, if I write that equation is R is equal to Q plus V, and then I need to multiply it by some sort of constant T to allow for it to change its magnitude. Not its direction, but its magnitude. Now, I'm also going to make that statement here. We can call it steps, or we can call it magnitude change, because it is going to be a scalar multiple. It's going to be a multiple of the velocity. So that's what that T represents. Now let's do another one. Let's create a new vector W, and let's create it such that W, let me use this color here, W is going to be at another angle. It does not need to be 90 degrees, it just needs to be another angle. Let's say this is W. But particularly, I'm going to make it a small vector like this. This is W. Hence, if I want to change W's magnitude or do multiple steps of W, I'm going to need another constant. Let's call it, this time, we'll call the constant K. So now I can move, let's say K is 1, 2, 3, 4, 5, 6, 7, 8, minus 1, minus 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see, therefore, that that is what this equation represents. But what's important here, and we'll end it in this with this discussion, is that I can now map out all of this plane in here. I can map that out, all of this. And the reason I can do that is because, for example, first of all, step 1, I can go to a point on the plane Q. So here's my point on the plane Q. Second of all, I can move in the direction of VT. Let's say I wanted to get to any point on the plane. Let's choose a point, this point X, somewhere close to the middle of this plane. Then what I can do is I can say, well, why don't we do T, I don't know, 5 times. 1, 2, 3, 4, 5. Nah, according to my diagram, actually, no, I said that was 10. So let's say this is about 4. So T becomes 4. So I've done V times T, and I've said 4. And then I'm going to do W, I don't know, I'm going to do W around and multiply it by around 5 times. So therefore W, which is this one here, remember, like I said at the beginning, I can move my vectors anywhere as long as I don't change the magnitude or the direction. So W, I'm going to move this W, let's keep the color the same for W, and say that from here, W looks like that. Right, so taking this W here, this one in here, that W, and I'm going to moved it to this position. Hence, if I multiply that W by, I said 5, let's say it goes something like 1, 2, 3, 4, 5, and there you have it. I was able to move to a point on the plane. Now I can do this by using any values of T and K, as long as they're real numbers. I can do negative, positive, decimals, whatever I wish to do. I can do that, and therefore I can say that I can move quite comfortably to this position with a multiple of T and K. I can move to this position, this position, this position. Y'all get my point. Technically, therefore, you can suggest that I can now move anywhere along this plane with this equation. And hence, this is the equation of a plane, wherein this is the equation, let's clean this one up a little bit. This is the equation of a line, this one here. And so, to conclude with this conversation, there is your equation of a line in the vector world. And here, a little bit messy, but let's simplify it somewhat by saying, I do believe it's here. Let's move slightly to the left so I can show you. It's not really the clearest one, so I'm going to type it. Let's type it. That in a 3D world, R equals q plus a vt plus, let's say, a wk. That would be the equation of a plane in there. Well, that's not that clear either, but that would be our equation of a plane. Oh, that's nice. And this would be our equation of a line. And hence, that will do for now, given that vectors is magnitude and direction, that we can utilize the ideas of the constant that's multiplied next to our vectors. Don't forget what these things represent. This q here is a representation of a position vector from the origin. This is along the line. This is a multiple of that vector v to move along the line. And if you need to do it in 3D space, then you need an extra vector at a different angle with an extra mechanism to multiply that vector so you can move wherever you wish. Right, that'll do for now. Thank you very much.